Hello everyone and welcome back. In this video, we're going to talk about buoyancy and Archimedes' principle. Let's start with a quick demo. You can try it yourself in your classroom or watch me run through it here. So what if we hang a 1 kilogram mass from a spring scale? What do you think that spring scale would weigh in newtons? 9.8? Yep, not surprisingly it does. But now, what do you think would happen if we dip this mass into a beaker of water? It weighs less. This is something that we need to know, that an object that is submerged or partially submerged in a fluid will weigh less than it does in air. And that's what this topic is about. So Archimedes, who lived in the BCs, reasoned that there must be an upward force acting on the object, and he named this upward force the buoyant force. So let's give the buoyant force a definition. The buoyant force is going to be the upward force that acts on any object that is submerged or partially submerged in a fluid. The variable for the buoyant force is going to be F with a lowercase subscript b, and it's going to be measured in newtons. So where does the buoyant force come from? The buoyant force arises due to the fact that there's pressure acting in all directions and that there's a pressure difference between the top and bottom of a submerged object. So for example, this here shows that we have pressure acting in all directions, pushing down, pushing up, pushing to the left, pushing to the right. Left and right forces aren't going to come into play right now. But because there's a pressure difference between the top and the bottom, we know that the pressure at point 2 is greater than the pressure at point 1. And the greater the pressure, the greater the force. So that tells me that I'm going to have a greater upward force than I am a downward force. And if I transfer that to a free body diagram, and I take this object and turn it into a dot over here, I have a greater upward force than I do a downward force. So you can visually see that there is a net force that is pointing up. I can also run through a quick calculation, quite simply, that the change in pressure, that pressure difference, is creating the force over the area. And that force, what I'm really looking for is the net force. So the change in pressure is PGH. But I have two different heights, so PGH2 minus PGH1, that pressure difference due to the height. And the area is pi r squared because the top area is the same as the bottom area. And through the calculation, I can see that I'm going to have a net upward force. And that net upward force has been named the buoyant force. Archimedes' principle tells us what the buoyant force is equal to. Archimedes' principle states that the buoyant force acting on an object is equal to the weight of the fluid displaced by the object. So let's look at this picture to try to explain what this means. So number one, we have an object here that is hanging from a spring scale, and you can see that it weighs 4 newtons. We are now going to submerge the object into this full container of fluid. And because the container is full, when we submerge the object, the water is going to spill out. The amount of water that spills out is going to be equal to the volume of the object. But Archimedes' principle says that the buoyant force is equal to the weight of the fluid displaced. So you can see here that the weight of this water is 3 newtons, which means that the buoyant force is 3 newtons. So if the buoyant force is 3 newtons, you can also see that the object, now that it's submerged in the fluid, weighs less. And this is called the apparent weight, FW, and then you put a little prime symbol there. FW prime is the apparent weight. And the apparent weight is what an object weighs under certain conditions. I want to be really careful that I don't say that apparent weight is what something appears to weigh, because it truly does only weigh 1 newtons when it's submerged. Another topic that we talked about apparent weight was back in dynamics, when we were talking about the weight of a person when they were accelerating up or down in an elevator. And their weight could increase or decrease because of those certain conditions. Let's look at this example. It says, given the picture, what is the apparent weight of the object? So we have a 5 kilogram mass hanging from a spring scale. And the first thing I think would be helpful to know is, what does this object weigh in air? So 5 times 9.8 is 49 newtons. In the second picture, we can see that when the object was submerged in the fluid, 2 kilograms of water spilled out. Well, Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. So the buoyant force is going to be equal to the weight. So I'm just changing the 2 kilograms into newtons. 2 times 9.8, 19.6 newtons. So then the question is, what is the apparent weight over here when I am hanging this from the spring scale? So we can figure this out by drawing like a free body diagram. And we have a weight of 49 newtons going down. We have a buoyant force of 19.6 newtons going up. So the apparent force is going to be the net force. So I'm going to take 49 minus 19.6, and I come up with an apparent weight of 29.4 newtons, which you can see is correct. So we have done that all conceptually just by understanding the definitions of those vocab words. Let's look at one more example. It says, given this picture, what is the buoyant force acting on the object? How about this time you try? Pause the video and click play when you're ready to resume. Okay, let's see how you did. So we can see from the picture that the object has a weight of 0.67 newtons. I'm looking for the buoyant force. I don't know how much, I don't know the weight of the spilled fluid. But I do see that the apparent weight is 0.4 newtons. So again, treating this kind of like an equation to guide my thinking. So I know that its actual weight in air is 0.67 newtons. There has to be an upward force acting on it that is giving me an apparent weight of 0.4 newtons. So the buoyant force is 0.27 newtons. Archimedes has his own claim to fame, and it's a story that all good physics students should know. Back in the day, and remember that Archimedes lived in the BCs, the king of the land wanted a new crown. So he gave some gold to the town's goldsmith, and the goldsmith made him a crown. But when he delivered the crown, the king became suspicious. How did he know if the crown was made of pure gold, or if maybe the goldsmith put some other metal in the crown and kept some of the gold for himself? So he summoned Archimedes, the smartest man in town. He directed Archimedes to determine whether the crown was pure gold or not. But the problem was, Archimedes didn't know how to do that. So Archimedes left with the crown in hand, but he had no plan. So the story goes that one day Archimedes was in town taking a bath. So remember, back then people didn't have bathrooms. They had to go to a public bathhouse in the middle of town to take a bath. So while sitting in the bathtub, it came to him. He figured out how to determine if the crown was pure gold or not. So he supposedly jumped from the bath and ran through the town naked, screaming, "Eureka!" which means I figured it out. To hear his solution and the ending of the story, please take a minute to click on the link provided or use the QR code to watch this 5-minute video. So how do we calculate the buoyant force? Let's derive the equation. So Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluids. That means that the buoyant force would be equal to the mass of the fluid times g. We could also get the mass from the density equation, and the mass of the fluid would be equal to the density of the fluid times the volume of the fluid. So let's replace this mass of fluid with this density equivalent. So that would give us this statement. And next, if we're submerging an object in a container of water, the amount of water that spills is going to be equal to the volume of the object. So we're going to replace this VF with a VO. And that would give us this statement here. This is the buoyant force equation. So you can calculate the buoyant force acting on something as long as you know the density of the fluid, in this case it would be water, 1,000, you'd have to know the volume of the object. If we're lucky, it'd be length times width times height, and 9.8. This may not have been exactly what Archimedes did, but this is one possible way to determine if the crown was made of pure gold. For example, suppose the crown had a mass of 2 kilograms. The density of gold is 19,300 kilogram per meter cubed. If the crown is then attached to a string and submerged in a container of water, we could calculate all of these things. So if we make the assumption that the crown is 100% gold, and then we get down here to the end and we predict the apparent weight when it's dipped in water, and that is the apparent weight, then we know it has to be pure gold. But if we assume it's pure gold and we do not get this apparent weight, then we know that other metal must have been mixed with the gold. So let's get into it. All right, let's look at part A. Part A says, what is the weight of the crown? So we can see here that the crown has a mass of 2, so the weight is going to be 2 times 9.8, or 19.6 newtons. Part B says, what is the expected volume of the crown? Well, we know the mass is 2, and we know the density of gold, so we could use the density equation to predict the volume of the crown. So density is mass over volume. That means that volume is going to end up being mass over density. I just cross multiplied. And so 2 divided by 19,300, and I get this very small number for volume. That number is very small because our units, meters cubed, are so large. All right, the next one, part C, says, what is the buoyant force acting on the crown? So the buoyant force is going to be the density of the fluid, that's 1,000, times the volume of the crown, it's dipped in the water, times 9.8, and the buoyant force is 1.02 newtons. So lastly, it says, what is the expected apparent weight of the crown? Well, let's go over here and draw a free body diagram. So if we have the weight pushing down, 19.6, and we have an upward buoyant force of 1.02, then we would expect a buoyant force of 18.58 newtons. And if we then dipped the crown in water and we did get an apparent weight of 18.58 newtons, then we know that it is made of pure